4.2 light-years. Every rocket humanity has ever built would take 80,000 years to cross that gap. Proxima b sits right there, the closest world that might hold life. And we already know the physics. We know the fuel math. We know what the radiation does to a body, what the isolation does to a mind, and what happens when a crew arrives with no fuel left to come home. If you find this mission briefing worth your time, subscribe. We launch new missions every week. Today we walk every waypoint of this journey: the propulsion traps, the deceleration problem, the planet that superflares everything alive, and the conclusion every serious engineer keeps reaching. Strap in, we depart now. Pull up the map. You are here, sitting inside a solar system at the edge of one arm of the Milky Way. The nearest star system to us is Alpha Centauri, and tucked inside it, orbiting a small red star called Proxima Centauri, is a planet, Proxima b, the closest world outside our solar system that scientists believe could, under the right conditions, support life. The distance between us and that planet is 4.2 light-years. That number sounds clean, clinical. It carries no weight until you convert it into something a human body can feel. Light travels at about 670 million miles per hour. In one single year, a beam of light covers roughly 5.9 trillion miles. 4.2 light-years means the distance to Proxima b is approximately 25 trillion miles. Write that out. 25 followed by 12 zeros. Every single mile of it is empty, hostile, and offers no margin for error. Now place yourself inside a spacecraft. The fastest object humanity has ever launched is the Parker Solar Probe, which reached speeds approaching 400,000 miles per hour on its closest approach to our star. Engineers celebrated that achievement. It was a genuine triumph of propulsion and thermal engineering. At that speed, reaching Proxima b would take roughly 6,500 years. Pause on that. Every civilization that has risen and collapsed in recorded human history fits inside that travel time. Ancient Egypt, Rome, the entire modern era, gone and forgotten twice over before the ship arrives. And the Parker Solar Probe reached that speed by using gravity assists, swinging around our star repeatedly to gain velocity. A ship heading toward Proxima b cannot do that. There is nothing out there to swing around. It accelerates, then coasts for thousands of years through absolute nothing. This is the baseline problem. Before we talk about fuel, radiation, food, or crew psychology, the raw geometry of the distance eliminates every propulsion system currently in operation on Earth. Chemical rockets, ion drives, solar sails in their current form, all of them produce a travel time measured in geological epochs, not human lifetimes. The mission demands a ship that travels at a meaningful fraction of the speed of light. Engineers use a rough threshold. To cross 4.2 light-years within a single human lifetime, the ship needs to sustain somewhere between 10 and 20% of light speed. At 20% of light speed, the journey takes about 20 months-years. Stripped down to bare physics, that seems achievable. Then you try to build the engine. Here is where the first wall appears. Reaching 20% of light speed requires an almost incomprehensible amount of energy. To give you a reference point, the energy needed to accelerate a crewed spacecraft to that velocity exceeds the total energy output of every power plant on Earth, running continuously for thousands of years. Every calculation engineers run to close that gap opens a new problem somewhere else in the system. And crossing the distance is only half the problem. The crew also has to stop. A ship screaming through interstellar space at 20% of light speed carries so much kinetic energy that without an equally powerful braking system, it flies straight through the Proxima Centauri system in hours and continues into the void forever. The crew survives the crossing. They just never land. The distance alone does not kill the mission outright. What it does is force every other system on the ship to perform at levels humanity has never come close to achieving. And as we move through each of those systems, the picture gets progressively darker. Because the propulsion problem, brutal as it is, turns out to be one of the easier ones to at least write equations for. Every crewed mission in human history ran on the same basic principle. Burn fuel, push exhaust out the back, move forward. It worked for reaching orbit. It worked for the moon. It worked for sending probes to the outer planets. Chemical propulsion is humanity's proven, tested, flight-rated technology, and it has an absolute ceiling that no amount of engineering refinement will ever break. That ceiling is exhaust velocity. When a chemical rocket burns fuel, the speed at which exhaust gases leave the engine determines how efficient the engine is. The best chemical engines ever built, using liquid hydrogen and liquid oxygen, produce exhaust velocities around 10 miles per second. That sounds fast until you compare it to what an interstellar mission requires. To reach even 1% of light speed, the spacecraft needs exhaust velocities thousands of times higher than anything a chemical reaction can produce. The energy stored in a chemical bond simply cannot release enough force per unit of mass. The physics do not bend for engineering ambition. But here is where it gets worse. And this is the part that ends the conversation for chemical propulsion permanently. A rocket must carry its own fuel. The more fuel it carries, the heavier it is. The heavier it is, the more fuel it needs to accelerate that mass. That cycle compounds on itself in what engineers call the Tsiolkovsky rocket equation, named after the Russian mathematician who derived it in 1897. The equation shows exactly how much propellant a rocket needs relative to its final velocity. Run the numbers for a chemical rocket aimed at Proxima b at 1% of light speed. A velocity still so slow the journey would take 420 years. The required fuel-to-payload ratio becomes so extreme that the ship would need to be almost entirely fueled by mass. We are talking about a structure where for every pound of actual spacecraft, crew, food, and equipment, you need millions of pounds of propellant. The total mass required exceeds anything conceivable to manufacture or launch. And 1% of light speed still means 4 centuries of travel. The crew's descendants would arrive, not the crew. A team at the California Institute of Technology ran updated projections on chemical propulsion for interstellar distances in the early 2000s and reached the same conclusion the rocket equation had already guaranteed. Chemical propulsion reaches its hard physical limit far below what any interstellar mission requires. The gap between what chemical engines produce and what the mission demands is so large that engineers stopped modeling it as an engineering challenge. They reclassified it as a physical boundary. This matters beyond just the propulsion question. Every system on a spacecraft designed for deep space depends on mass budgets. Every pound of extra fuel means less room for food, water recycling systems, medical equipment, shielding, and crew. Chemical propulsion is so inefficient at the velocities required that even fitting the fuel on board becomes structurally impossible before you even ask whether the crew can survive the journey. Voyager 1, launched in 1977, is the most distant human-made object ever built. It is currently about 15 billion miles from Earth, traveling at roughly 35,000 miles per hour. At that speed, it would take approximately 73,000 years to reach Proxima b's distance. It used chemical rockets to launch and gravity assists from Jupiter and Saturn to gain speed. Those options are not available on an outbound interstellar trajectory. Engineers knew chemical propulsion was off the table before the space age was 20 years old. The search for a replacement has been running for decades. Some proposals are brilliant. Several are physically sound. All of them carry a cost that changes the nature of the mission in ways the fuel problem alone never does. What replaced chemical rockets on the drawing board is something far more violent, far more powerful, and far more politically complicated than burning hydrogen and oxygen ever was. In the late 1950s, a group of physicists and engineers at General Atomics in California sat down and asked a direct question. If chemical rockets cannot produce the exhaust velocity an interstellar mission needs, what is the most energetic reaction a human team could actually control and use for propulsion? The answer they landed on was nuclear detonation. Project Orion, as the program was named, proposed a spacecraft that would accelerate by detonating a sequence of nuclear bombs directly behind it. A thick steel plate called a pusher plate, mounted at the rear of the ship, would absorb the blast and convert it into forward momentum. A system of shock absorbers between the plate and the crew section would smooth the impulse so the people inside experienced something closer to a firm push than an explosion. The concept sounds extreme. It was extreme. It was also, by every engineering calculation the team ran, physically workable. Freeman Dyson, one of the most respected physicists of the 20th century, joined the project and spent years refining the numbers. His calculations showed that an Orion-class spacecraft using nuclear pulse propulsion could reach speeds between 3 and 10% of light speed. At 3%, the journey to Proxima b takes about 140 years. At 10%, it drops to around 42 years. Those numbers put the mission inside the range of a multi-generational crewed voyage, or potentially a single extended lifetime with the right crew age selection. The fuel source, nuclear bombs, is the part that makes modern engineers wince. Each pulse would require a dedicated bomb, ejected behind the ship, detonated at a precise distance and timing. The Orion team estimated a ship built for interstellar travel would need hundreds of thousands of them, stored in an onboard magazine and fed to the ejection system continuously. The bombs were small by weapons standards, but the quantity required was staggering. Here is what made Orion genuinely different from every other proposal on the table. The engineering team built scale models. They tested pusher plate dynamics with chemical explosions in the Nevada desert. The plate worked. The shock absorption worked. The momentum transfer worked. This was a program that moved beyond equations into physical hardware tests, and the hardware held up. Then the Partial Nuclear Test Ban Treaty arrived in 1963. The treaty banned nuclear detonations in the atmosphere, in space, and underwater. Orion required detonations in space. The program ended. Dyson later called it one of the great engineering tragedies of the 20th century. A propulsion system that the physics and the hardware both validated, shut down by a political agreement that had nothing to do with whether the engine could work. Modified descendants of the Orion concept have been studied since, including Project Daedalus in the 1970s, which used nuclear fusion microexplosions rather than bomb detonations. The principle is similar. Use the most energy-dense reaction available to humans and direct it rearward. The specific impulse, the measure of engine efficiency, is thousands of times higher than any chemical rocket. But every version of nuclear pulse propulsion carries the same unresolved problem. The ship must carry an enormous number of fuel units, whether bombs or fusion pellets, and that mass must be launched off Earth or assembled in orbit before the mission begins. The infrastructure required to manufacture and store that much nuclear fuel exceeds anything currently in existence by several orders of magnitude. The engine worked. The factory to build its fuel does not exist. And even if it did, the crew inside that ship faces a threat that has nothing to do with the engine, the fuel, or the bombs. It comes from space itself, and it begins the moment the ship leaves the protection of Earth's magnetic field. In April 2016, a group of scientists and investors announced a program called Breakthrough Starshot, with a combined funding commitment of $100 million. The goal was to send a spacecraft to Proxima Centauri within a generation. The proposed vehicle was a light sail, a thin reflective sheet roughly a few meters across, attached to a payload the size of a microchip. The propulsion system was a ground-based laser array producing 100 gigawatts of focused power, beamed at the sail for a few minutes. The physics, confirmed by multiple independent teams, showed the sail could reach 20% of light speed. Travel time to Proxima b, roughly 20 years. Engineers called it the most credible fast interstellar proposal ever formally studied. The laser array is theoretically buildable. The sail material, a reflective film a few hundred atoms thick, is within reach of current manufacturing. The payload, a gram-scale chip carrying cameras, sensors, and a transmitter, fits inside achievable miniaturization targets. The team published a detailed technical roadmap and identified no physics violations in the core concept. There is one detail they were transparent about from the beginning. The system cannot carry a crew. At 20% of light speed, a human body requires gradual acceleration over a manageable period, which demands a propulsion system that sustains thrust for extended time. The laser sail accelerates in minutes. The gravitational force on anything inside that sail during that acceleration window would be hundreds of times the force of Earth's gravity. Every organ in a human body would compress and rupture. A person cannot survive the launch phase. The payload limit also makes crewed flight physically impossible under this architecture. The sail works because it is essentially weightless. Add a life support system, food stores, water, medical equipment, shielding, and a human body, and the mass increases by many orders of magnitude. The laser array required to push that mass to 20% of light speed would need to be so powerful it would vaporize the sail and everything attached to it before it reached speed. Breakthrough Starshot is a genuine engineering program. It is the most advanced formal study of fast interstellar travel in history. And it confirms, precisely and intentionally, that moving a living crew across interstellar distances at the speeds required falls outside what the concept can address. The probes it sends, if built and launched, would arrive at Proxima b in about 20 years. They would take photos, measure the atmosphere, scan for biosignatures, and transmit the data home. That data would arrive on Earth roughly 4 years after the probe reaches the system. Scientists alive today might read it. Those probes would carry no crew and have no ability to slow down. They would cross the Proxima Centauri system in hours and continue into deep space. A flyby at 20% of light speed lasts minutes. Everything the probe observes, it must record and transmit in that window. A crewed mission requires arriving, decelerating, achieving orbit, and landing. Every one of those steps demands energy the sail system cannot provide. The Starshot architecture solves the crossing problem and deliberately leaves everything else unsolved, because solving everything else would collapse the design back to the same mass and energy constraints that killed every other proposal. The fastest credible interstellar system ever formally studied confirms that speed and crew survival are, under current physics, mutually exclusive at interstellar distances. What happens to a human body at a fraction of those speeds, sustained over years rather than minutes, is a separate problem entirely. And the answer is something the medical data has been building toward for decades. Forget the destination for a moment. Focus on the first few hours of the journey. Any spacecraft capable of reaching 20% of light speed within a travel time a crew can survive must accelerate hard. Sustained acceleration is the only way to build velocity. Engineers typically model interstellar mission profiles using a constant 1 gravity of acceleration, meaning the ship pushes forward at the same rate Earth's gravity pulls you down. At 1 gravity, you feel normal. Your blood circulates. Your bones bear weight. Your cardiovascular system functions as designed. At 1 gravity of constant acceleration, a ship reaches 20% of light speed in about 60 days. That is workable. The crew stays physically healthy during the burn phase. This is actually the optimistic scenario mission planners use as a baseline. The problem is what 1 gravity of constant acceleration demands from the propulsion system over 60 days. The force required to sustain 1 gravity of acceleration on a crewed spacecraft, which must carry life support, shielding, food, water, and equipment, requires an engine output that exceeds every propulsion concept currently beyond the early design stage. The nuclear pulse systems that could theoretically reach those velocities do so through intense, discrete bursts, each one a hammer blow. Sustained smooth acceleration at 1 gravity is a different engineering target entirely, and a far harder one. Now consider what happens if the propulsion system cannot sustain 1 gravity. If the mission profile requires higher acceleration over a shorter window to achieve the same final speed, the forces multiply fast. At 5 gravities of acceleration, a trained astronaut can remain conscious for short periods. Military pilots in high-performance aircraft train extensively to survive brief exposures at those levels, using compression suits and practiced muscle techniques. Sustained exposure at 5 gravities causes blood to pool away from the brain. Vision narrows to a tunnel, and loss of consciousness follows within seconds without a pressurized suit. At 10 gravities, no amount of training or equipment keeps a person functional. Internal organs shift. Blood vessels in the eyes rupture. The diaphragm struggles to expand against the compressive force, making breathing labored and eventually impossible. Sustained exposure at this level causes internal bleeding and organ failure. At the acceleration levels the breakthrough Starshot sail experiences during its laser-driven launch, the gravitational equivalent exceeds tens of thousands of times Earth's gravity for several minutes. A human being at those levels does not die. The body simply stops being a body in any recognizable structural sense. Even at civilized, manageable acceleration profiles, a crewed interstellar mission faces a secondary physiological crisis that builds slowly over the entire journey. Microgravity, or the very low effective gravity experienced during the long coasting phase, after the engine cuts off, dismantles the human skeleton and cardiovascular system over months and years. Research from long-duration missions aboard the International Space Station, confirmed across dozens of crew members, shows that after 6 months in microgravity, the average astronaut loses significant bone density, particularly in the hips and lower spine. Muscle mass degrades, the cardiovascular system weakens, because the heart no longer works against gravity. Fluid shifts toward the head, raising intracranial pressure and degrading vision in ways that persist long after return to Earth. A mission to Proxima b, at manageable acceleration, takes at minimum 20 years in transit, with a long coasting phase in microgravity. The crew that arrives, if the ship reaches its destination, may be physically incapable of the surface operations the mission requires. And acceleration and microgravity are only the beginning of what the journey does to a human body. Something the ship cannot outrun starts the moment it clears the heliopause. It travels at the speed of light, and it comes from every direction at once. There is no shelter from it, no speed that outruns it, no material currently in production that stops it completely. Cosmic radiation is the background condition of interstellar space, and it is incompatible with human biology at the exposure levels a multi-decade voyage produces. On Earth, the planet's magnetic field deflects the majority of high-energy charged particles, streaming in from deep space. The atmosphere absorbs most of what gets through. A person living their entire life on the surface receives a radiation dose low enough that the body's natural repair mechanisms handle it continuously without catastrophic accumulation. Astronauts aboard the International Space Station, in low Earth orbit where the magnetic field still provides partial shielding, receive radiation doses roughly equivalent to several chest X-rays per day. Long-duration crew members typically complete 6-month rotations, specifically because radiation exposure guidelines set limits on cumulative dose. Even at that distance, staying longer carries increasing cancer risk. Beyond the magnetic field, in open interstellar space, the radiation environment intensifies dramatically. Two primary sources dominate. Galactic cosmic rays are high-energy particles, mostly protons and atomic nuclei, accelerated to near-light speed by supernova shockwaves across the galaxy. They arrive continuously from every direction with enough energy to penetrate several feet of aluminum. The second source is solar particle events from stellar activity. Though once far enough from our star, galactic cosmic rays become the dominant threat. A team at NASA's Johnson Space Center modeled radiation exposure for a crewed Mars mission, which covers a fraction of the distance to Proxima b, and concluded that round-trip exposure would approach or exceed the career lifetime limits set for astronauts under current safety guidelines. The Mars mission takes roughly 3 years. An interstellar mission takes 20 or more. Scaling the exposure time gives a radiation dose over a 20-year transit that current safety models classify as producing near-certain radiation-induced cancer in the majority of crew members before arrival. The high-energy particles also penetrate the brain and central nervous system. Confirmed research from accelerator experiments designed to simulate cosmic ray exposure shows measurable cognitive impairment in animal subjects after prolonged bombardment, including memory degradation and reduced ability to process new information. Shielding is the obvious answer. Every engineering team studying the problem reaches the same conclusion about shielding: mass. Dense material absorbs radiation, and the more mass between the particle and the crew, the better the protection. Water is a reasonable shielding material. Polyethylene, a hydrogen-rich plastic, performs well. Lead blocks lower energy radiation, but fails against galactic cosmic rays, which carry so much energy they generate secondary radiation when they hit dense material, producing a cascade of particles inside the shielding itself. Building a radiation shield sufficient to protect a crew over 20 years in interstellar space requires surrounding the crew module with meters of material. That mass is enormous, and every kilogram of shielding is a kilogram the propulsion system must accelerate to 20% of light speed, which exponentially increases the fuel required, which increases the mass further. The shielding problem and the propulsion problem feed each other in a cycle that current engineering cannot close. Radiation kills slowly. It accumulates in the genome, damages cellular repair mechanisms, and raises cancer probability with every day of exposure. A crew could complete the 20-year crossing and arrive at Proxima b already carrying terminal diagnoses from the journey itself. And radiation is a problem we at least know how to measure. What the ship encounters at speed, in the interstellar medium, is something the crew cannot shield against, cannot navigate around, and cannot slow down to avoid. Space looks empty. The images show black void between stars, and that description is accurate enough at low speeds. At 20% of light speed, the interstellar medium transforms into something the engineering community has no complete solution for. Between the stars, space contains a diffuse scattering of particles: hydrogen atoms, helium atoms, electrons, dust grains, and microscopic debris. The average density is extraordinarily low, roughly 1 atom per cubic centimeter in most regions. If you filled a container the size of a school gymnasium with interstellar medium collected from between stars, you would have roughly as many particles as in a matchbox of Earth's atmosphere. At human walking speeds or even satellite orbital speeds, this density is irrelevant. Particles hit the spacecraft's surface at such low relative velocities that the energy transfer is negligible. At 20% of light speed, each hydrogen atom the ship runs into carries the kinetic energy of a high-velocity rifle round. The ship does not move through space, and occasionally hit a particle. At that speed, the interstellar medium is a continuous rain of projectiles hitting every square inch of the forward surface, simultaneously. A team of physicists published calculations in 2015, specifically examining this problem for the breakthrough Starshot sail concept. They found that a sail crossing 4.2 light-years at 20% of light speed would absorb enough particle impacts to erode the forward surface significantly, degrading its reflectivity and structural integrity during transit. For a gram-scaled ship, engineers can design redundant electronics and accept some surface erosion. For a crewed spacecraft with a large forward cross-section, the erosion problem scales to an entirely different magnitude. The dust grains are the worst of it. Even particles a fraction of a millimeter across carry enough energy at these speeds to punch through standard spacecraft hull material. A crewed ship needs a forward shield capable of absorbing decades of continuous micro-impacts without structural failure. The designs proposed, typically a sacrificial layer of beryllium or graphite, many centimeters thick, add enormous mass to the bow of the spacecraft. That mass must be accelerated, which means more fuel. The fuel problem expands again. Engineers at the Institute for Advanced Concepts studied electromagnetic shielding as an alternative, creating a magnetic field ahead of the ship to deflect charged particles around the hull. It works for ions. It does nothing for electrically neutral hydrogen atoms or dust grains, which make up a significant fraction of the interstellar medium. There is a proposed concept called a magnetic scoop, or Bussard ramjet, named after physicist Robert Bussard, who described it in 1960. The idea is elegant. Instead of carrying fuel, the ship scoops hydrogen from the interstellar medium as it travels, and uses it as fusion fuel. The faster it goes, the more hydrogen it scoops, the more fuel it has. Theoretically, it could accelerate indefinitely. The problem, identified by later analysis, is that the drag created by scooping interstellar hydrogen at the densities actually measured between stars produces more braking force than the fusion reaction generates in thrust. The ramjet decelerates itself. The concept, beloved by science fiction for decades, does not survive contact with the measured density of the interstellar medium. Every method of handling the particle flux at interstellar speeds either adds mass, fails against neutral particles, or actively slows the ship down. The medium between stars is not empty. It is an obstacle course, and the faster you move through it, the more dangerous every particle becomes. Getting through the interstellar medium is solvable, engineers argue, if you accept the mass penalty. But the destination has its own threat waiting, one that starts long before the ship arrives and has been firing continuously for billions of years. Here is the trap that closes around every interstellar mission design. the one that engineers keep arriving at no matter which propulsion system they start with. Accelerating to 20% of light speed is brutal. The energy requirements are enormous. The mass of fuel needed staggers the imagination. But every calculation that produces a credible crossing time of 20 to 40 years faces an identical problem on the other end of the journey. The ship must stop. A spacecraft crossing 25 trillion miles at 20% of light speed carries kinetic energy proportional to its mass and the square of its velocity. When velocity is 20% of light speed, the kinetic energy carried by even a modest spacecraft mass is tremendous. To bleed off that energy and come to rest relative to Proxima b, the ship must apply force in the opposite direction of travel for a sustained period equivalent to the acceleration phase. That means the ship must carry enough fuel to decelerate the entire mass of the ship, including the crew, the life support systems, the equipment, and crucially, all the deceleration fuel itself. This is the same compounding problem as launch, but applied to a ship already traveling at a significant fraction of light speed, far from any star that could provide a gravitational assist. Robert Zubrin, an aerospace engineer who has spent decades designing Mars mission architectures, analyzed the fuel requirements for a crewed interstellar mission with full deceleration capacity. His calculations, using fusion propulsion as the assumed engine, showed that the ratio of initial fuel mass to final payload mass becomes so extreme that the required launch mass exceeds any realistic manufacturing or launch infrastructure by factors of thousands. The cleanest summary: to carry enough fuel to stop, you need so much fuel that you cannot carry enough fuel to stop. Engineers call this the tyranny of the rocket equation. It applies at every scale. The more mass the mission requires, the more fuel it needs, and the fuel itself is mass. The equation spirals upward without limit. 3 conceptual solutions exist, and each trades one impossible requirement for another. The first is staged propulsion. The ship uses a first stage to accelerate, jettisons it, and a separate braking system handles deceleration at the destination. This requires either pre-positioning a braking system at Proxima b before the crewed mission, which takes thousands of years using current technology, or carrying the entire braking apparatus as cargo, which brings the mass problem back in full. The second is in situ resource utilization, meaning the ship mines fuel from the Proxima Centauri system after arrival. This assumes the system contains accessible fuel in a form the ship can process, a completely unverified assumption for a system we have never directly observed at close range. The third is what Breakthrough Starshot implicitly accepts: skip deceleration entirely. Send a probe that flies through and keeps going. For a crewed mission, this is not an option. A crew that cannot stop cannot land. Every credible crewed interstellar mission study ever published acknowledges the deceleration problem explicitly. Most propose fuel ratios that would require launching a structure heavier than a large warship from Earth's surface, which is currently impossible. Some propose assembling the fuel in orbit over decades. All of them treat deceleration as an open engineering problem without a closed solution. There is one proposed system that sidesteps the onboard fuel requirement for braking. It uses the destination star itself as the brake, and the physics behind it are real. But the scale of engineering required to build it makes the ship itself look simple by comparison. If a ship cannot carry enough fuel to decelerate at Proxima Centauri, and if flying through without stopping is unacceptable for a crewed mission, then the braking force must come from somewhere external. Physicist Dana Andrews and engineer Robert Zubrin proposed a concept in the early 1990s that uses something already present at the destination: the stellar wind. Every star continuously ejects a stream of charged particles outward in all directions. Around our own star, this stream, called the solar wind, extends for billions of miles and creates the heliosphere, the bubble of charged particle influence that Voyager 1 crossed in 2012. Proxima Centauri produces its own stellar wind. A magnetic sail works by generating a powerful electromagnetic field ahead of the ship. This field deflects the incoming stellar wind particles, and the resulting pressure pushes back against the ship. If the ship is moving toward the star, the stellar wind hits the magnetic field from the front, and the drag that creates bleeds off velocity. The ship brakes against the wind of the destination star, without burning a single kilogram of onboard fuel. The physics are confirmed. Magnetic sails work within the bounds of established electrodynamics. A team at the University of Alabama in Huntsville ran detailed engineering models in the 2000s and confirmed the braking principle is sound. The engineering requirement is where the concept produces its next impossible number. To generate a magnetic field strong enough to provide meaningful braking force on a spacecraft crossing interstellar distances, the field must extend for a very large radius around the ship. The calculations show that a magnetic sail capable of decelerating a modest crewed spacecraft from 20% of light speed to orbital velocity around Proxima b requires a field radius of several hundred miles. Creating that field requires a superconducting loop of wire carrying enormous electrical current. That loop, even using the most advanced superconducting materials currently under development, would need to be hundreds of miles in diameter. The mass of the wire alone, even at the thinnest viable gauge, would be measured in thousands of tons. Deploying a structure that size in interstellar space and keeping it stable at the magnetic field strengths required involves engineering challenges that no current program has even begun to prototype. The concept also requires the ship to enter the Proxima Centauri stellar wind far enough out that the braking distance is sufficient. At 20% of light speed, the ship covers enormous distances quickly. The braking must begin at an enormous distance from the star to allow the deceleration curve to bring the ship to orbital velocity before it overshoots. If the field deploys too late, the ship enters the braking phase with insufficient distance to stop and passes through the system regardless, timing a deployment sequence for a structure hundreds of miles across. Traveling at 20% of light speed, after a 20-year crossing of interstellar space, with no maintenance crew and no external support, requires an autonomous system's reliability that engineering has never demonstrated over anything close to that time horizon. The magnetic sail is the best braking concept currently on the table. The physics are real. The engineering requirement is a loop the size of a small country deployed in deep space by a fully autonomous system that has operated without failure for 2 decades. And if the crew manages all of that, if the ship accelerates, crosses the interstellar medium intact, and decelerates into the Proxima Centauri system, what they find waiting around that red star has been preparing a hostile reception for billions of years. Proxima Centauri is a red dwarf star. Red dwarfs are the most common type of star in the galaxy, smaller and cooler than our own, burning their fuel so slowly they can live for trillions of years. They sound gentle. They sound stable. They are not. Red dwarfs, particularly young and middle-aged ones, produce superflares, eruptions of radiation, and charged particles from their surface that dwarf anything observed from larger, calmer stars. Research published in 2019, drawing on observations from multiple space telescopes, confirmed that Proxima Centauri produces superflares regularly, sometimes several per day, during active periods. A typical superflare from Proxima Centauri releases energy equivalent to millions of nuclear weapons, detonating simultaneously in the form of X-rays, ultraviolet radiation, and high-energy charged particles. The burst propagates outward at a significant fraction of light speed and arrives at Proxima b within seconds to minutes of the flare's peak. Proxima b orbits Proxima Centauri at a distance of roughly 4.7 million miles. This tight orbit is what gives the planet any chance of liquid water temperatures, despite the star's dim output. But that closeness means Proxima b sits inside the most violent zone of the star's activity. The planet receives flare radiation at intensities that calculations show would strip lighter atmospheric gases over geological timescales and bombard any surface with radiation doses lethal to most Earth organisms during each major event. For comparison, our own star produces powerful flares, and even a strong event directed at Earth is partially deflected by the planet's magnetic field and absorbed by the thick atmosphere. Proxima b's magnetic field strength is unknown, and models of planetary magnetic fields for tidally locked worlds like Proxima b suggest it may be weak or irregular. If the planet's magnetic shield is compromised, superflares hit the surface essentially unimpeded. The 2019 study estimated that a person standing on the surface of Proxima b during a major superflare without substantial shielding would receive a lethal radiation dose within minutes. A crewed ship in orbit around Proxima b during a superflare event faces the same threat from a different angle. The crew compartment requires shielding effective enough to protect against the ship's transit radiation environment. A superflare delivers a dose on a compressed timescale, spike radiation instead of background radiation, and the required shielding thickness for spike events is significantly higher than for continuous low-level exposure. The star flares regularly. The crew cannot predict every event. The ship cannot simply leave orbit during a flare, because departure burns take time to plan and execute. The crew needs a dedicated storm shelter inside the ship, a heavily shielded compartment small enough to be protected by dense material, where every person aboard retreats for the duration of each major flare event. That storm shelter adds mass. Everything adds mass. The mass equation keeps growing, and the star's violence is only half the problem with the Proxima Centauri system. The planet itself, Proxima b, may have spent billions of years shaped by those flares into something that bears no resemblance to the habitable world mission planners hope to find. What those superflares have done to the planet's atmosphere over the billions of years the star has been active is a question scientists are actively debating. The answer changes everything about whether the mission has any surface to land on worth reaching. The mission travels 25 trillion miles. The crew survives the radiation, the isolation, the fuel constraints, and the deceleration burn. The ship achieves orbit around Proxima b. And then the most basic question, the one the entire mission hangs on, gets answered by the instruments for the first time. Does this planet have an atmosphere? Scientists do not know. This is confirmed uncertainty, not a gap that will close before a mission launches. As of the most recent atmospheric modeling studies, Proxima b's atmospheric status sits in a range that spans from rich nitrogen-oxygen envelope similar to Earth's to completely stripped bare rock with no atmosphere at all. The mechanism doing the stripping is the superflare activity described in the previous chapter. When a massive flare hits a planet, the radiation and charged particle stream interact with the upper atmosphere. Lighter molecules, particularly hydrogen and helium, receive enough energy to reach escape velocity and leak out into space. Over millions of years, a flare-active star can erode a planet's atmosphere from the top down. For Proxima b, which has orbited inside the active zone of a superflare-producing star for an estimated 4 billion years, the cumulative erosion could be severe. A study from the Goddard Space Flight Center estimated that Proxima b may have lost the equivalent of several Earth atmospheres worth of material over its history. Whether enough gas remains to constitute a functional atmosphere depends on factors the planet itself controls, primarily volcanic outgassing. If Proxima b has active geology, erupting volcanoes continuously pump gas back into the atmosphere from below, while the star strips it from above. The net result could be a thin but present atmosphere, or an equilibrium that maintains a breathable envelope over geological time. If the planet is geologically dead, the stripping wins, the atmosphere gets thinner every century. Astronomers have attempted to detect Proxima b's atmosphere through a technique called transmission spectroscopy, observing how the planet's silhouette filters starlight during transits to identify chemical signatures. Proxima b does not transit its star at an angle visible from Earth, making this technique inapplicable. Direct atmospheric measurement requires a telescope in the Proxima Centauri system, or an instrument far more powerful than any currently built or funded. The mission crew arriving in orbit around Proxima b would be the first instruments capable of answering the question directly. If the atmosphere is thick enough to land in, a surface mission becomes possible with proper protective equipment against radiation. If the atmosphere is thin, landing means operating in near vacuum with full pressure suits, and any hope of the planet sustaining biology diminishes sharply. If there is no atmosphere, the surface is a hard vacuum irradiated by superflares without any protective filtering. Landing is possible with engineering. Survival without a sealed habitat is immediate death. The crew would not know which scenario they were arriving into until they got there. 20 years of travel, and the first orbital scan answers the foundational question the mission was built on. Whatever that scan reveals, the surface environment is shaped by one more planetary characteristic that Proxima b almost certainly shares with every planet orbiting this close to its star. It is a characteristic that splits the world into two permanently opposed extremes, and leaves almost nowhere in between. Proxima b orbits its star in 11.2 Earth days. That is its year. A complete trip around Proxima Centauri takes less than 2 Earth weeks. The orbit is so tight, the gravitational pull so persistent and uneven across the planet's diameter, that over billions of years, the star's gravity has synchronized the planet's rotation with its orbit. Proxima b almost certainly keeps one face permanently pointed toward its star, and one face permanently pointed away. The same hemisphere bakes in continuous starlight forever. The opposite hemisphere sits in permanent darkness and cold. This is called tidal locking, and the moon demonstrates it to us every day, always showing Earth the same face for exactly this reason. On a tidally locked planet, the day side receives constant stellar radiation with no night cycle to cool it. Temperatures on the day side can reach levels where rock liquefies, depending on atmospheric pressure and composition. The night side, receiving no direct radiation, cools to temperatures approaching those of deep space near the surface. Models estimate Proxima b's night side could reach hundreds of degrees below 0 Fahrenheit in the absence of a thick atmosphere to circulate heat. The terminator, the boundary line between eternal day and eternal night, forms a continuous ring around the planet where the star sits permanently on the horizon. This zone receives angled, gentle stellar radiation rather than direct overhead bombardment. Atmospheric circulation models show that if Proxima b has a substantial atmosphere, wind patterns carry heat from the day side toward the night side continuously, and the terminator region may be the most temperate band on the entire planet. This is where mission planners focus surface landing scenarios. The terminator zone is theoretically the most survivable band on the planet, receiving moderate temperatures, protection from direct overhead flare bombardment by the angle of incoming radiation, and potentially some atmospheric mixing that moderates extremes. The terminator zone on Proxima b would be a narrow band, perhaps a few hundred miles wide, where temperatures might fall in a range between deeply cold and uncomfortably hot, depending on local geography and atmospheric thickness. Crew operations would concentrate in this band. But the tidal locking creates engineering problems beyond surface temperature. Atmospheric circulation, driven by the permanent temperature gradient between day side and night side, produces permanent storm systems at the terminator. Wind speeds in these circulation cells could be extreme, powered by the continuous heat differential. Landing a spacecraft in high winds with no ability to choose a weather window, because no weather window exists in a permanently fixed atmospheric system, complicates descent and surface operations significantly. Navigation on a tidally locked world is also disorienting by Earth standards. The star never rises or sets. It sits at a fixed point in the sky, motionless. Day, night, and the cycle of time that all human biology runs on disappears entirely. Circadian rhythms, the internal biological clock humans and most organisms use to regulate sleep, hormone production, and cellular repair, would have no external signal to synchronize with. After extended surface operations, biological rhythm disruption adds to the cumulative physiological load the crew already carries. The surface environment on Proxima b is shaped by forces that do not exist on Earth, and that human biology was never built to handle. And the crew standing in the terminator zone, looking up at a sky where the star never moves, would be looking at a world shaped by those forces for billions of years. What that surface actually looks like beneath their boots, and what the gravity, geology, and atmospheric chemistry do to their bodies during a surface stay, is something no Earth-based simulation has ever reproduced with fidelity. The ship achieves orbit. The scans run. The crew looks at the data and makes a decision no mission controller on Earth can make for them, because the signal lag means any question they transmit home will receive an answer 8.4 years later. They are alone with the information, and they choose whether to descend. Proxima b has a mass estimated at a minimum of 1.3 times Earth's mass. If the planet is rocky, as most models predict for a world at this orbital distance around a red dwarf, the surface gravity is likely higher than Earth's, somewhere in the range of 1 to 1.5 times Earth's gravity. After 20 years in microgravity transit, the crew's bones and muscles are significantly degraded, They step onto a world that pulls harder than the one they left, with bodies weaker than the ones they launched with. The surface geology is unknown. No probe has visited. No telescope has resolved the surface. The crew's orbital instruments provide some atmospheric chemistry data and surface temperature mapping, but the ground beneath the landing site is a first contact scenario with no prior survey data. Rocky planets in the habitable zones of red dwarfs go through intense volcanic activity early in their formation, driven by tidal heating from the star's gravitational flexing of the planet's interior. Whether Proxima b still has active volcanism or has cooled to a geologically quiet state determines whether the atmosphere is being replenished and whether the surface is stable underfoot or riddled with fissures and lava flows. The surface chemistry is a primary mission question. If volcanic outgassing has produced an atmosphere containing sulfur dioxide, carbon monoxide, or other toxic compounds, crew operations outside a sealed suit become more hazardous. Identifying breathable gas ratios from orbit requires instruments the ship carries, and the results shape every surface decision the crew makes. Water is the central question. Liquid water requires a specific atmospheric pressure range to remain stable at the surface. If pressure is too low, water sublimates directly to vapor. If temperatures on the terminator are in the right range and atmospheric pressure is sufficient, liquid water is possible. The crew searches for it the way a surgeon searches for a pulse. Everything downstream depends on the answer. Proxima b's surface could contain oceans on the day side, kept liquid by continuous stellar heating, with ice sheets covering the night side. Atmospheric models from a team at the University of Exeter, published in 2017, showed that a planet with Proxima b's parameters and a thick enough nitrogen atmosphere could sustain a temperate belt of liquid water near the terminator. This remains a model, a prediction, confirmed by the math of fluid dynamics and atmospheric physics, unconfirmed by any direct observation. The crew lands at the terminator. The ground beneath them is either the first step toward a new branch of human civilization or a dead rock under a violent star. The instruments tell them which. And whatever the surface reveals, the crew processes that information with minds that have been sealed inside a metal hull for 2 decades, cut off from Earth, from resupply, from rescue. The psychological weight of that isolation, building across every year of the crossing, does not disappear when the landing gear touches down. It has been accumulating since departure, and the science of what it does to a human mind is something no mission plan has ever adequately solved. 6 months. That is the standard duration for a single crew rotation aboard the International Space Station, and the psychological research from those missions fills entire journals. Isolation stress, interpersonal conflict, attention fatigue, decision fatigue, and what researchers call third quarter phenomenon, where morale and performance dip sharply in the final phase of a long mission, all appear consistently across decades of crew data. 6 months. The Proxima mission lasts 20 years in transit, minimum, then an indeterminate surface mission, then if a return trip is even possible, another 20 years back. Psychologists at NASA's Human Research Program have studied isolation and confinement rigorously, including through the Hawaii Space Exploration Analog and Simulation missions, where crews lived in sealed habitats on a Hawaiian lava field for up to a year to simulate interplanetary isolation. The results show that even highly trained, carefully selected individuals experience measurable psychological deterioration over 12-month confinements. Sleep patterns destabilize. Interpersonal tensions escalate over minor irritants that become enormous in a small space with no escape. Decision-making quality degrades. Crews develop what psychologists call behavioral drift, a gradual loosening of formal communication and mission protocols that can undermine safety margins. In every long-duration analog study, the point at which behavioral drift becomes operationally dangerous moves earlier and earlier as mission duration extends. A 20-year transit in a sealed hull presents a psychological environment with no analog in human experience. No culture, no civilization. No religion has prepared a framework for what it means to spend 2 decades in a pressurized cylinder with the same group of people, with no privacy, no meaningful external environment, no fresh stimulation. and no connection to the world left behind except time-delayed messages. The crew would watch Earth recede to a point of light and then disappear entirely within the first year. They would communicate with family and colleagues through messages delayed by increasing years each way. A crew member who sends a message to their child receives the reply when that child is several years older. Over time, the correspondence becomes a relationship conducted across such large time gaps that its emotional sustenance diminishes. Mission planners propose addressing psychological health through rotating crew roles, carefully curated entertainment archives, structured social programming, and private communication channels. These tools help. The research shows they do not eliminate the fundamental problem of duration and isolation. The crew that reaches Proxima b after 20 years together in a sealed environment is a psychologically altered group. Their relationships have been under pressure for 2 decades. Their cognitive patterns have adapted to an unchanging environment. Their capacity for the flexible, rapid decision-making that surface exploration in an unknown environment demands is a resource that has been drawn on continuously and cannot be fully restored without the one thing the mission cannot provide: genuine change of scene and genuine rest. The psychological challenge of the transit is solvable enough that mission designers include it in their frameworks. What it is not is small, and it sits on top of the physiological degradation, the radiation exposure, and the cumulative engineering failures that accumulate over 20 years of continuous operation with no repair support. Because the ship itself, every system, every wire, every seal, and every circuit has also been running for 20 years, and machines, like people, do not survive that duration unchanged. Every machine fails. The question engineering answers is how often, how badly, and what happens next. On Earth, a machine that breaks gets repaired. A part that wears out gets replaced. A system that degrades gets rebuilt by a maintenance crew, with access to a supply chain stretching back through thousands of suppliers and decades of manufacturing capability. On a spacecraft 25 trillion miles from the nearest hardware store, none of that exists. Every component that breaks must be fixed with what is aboard. Every part that wears out must be fabricated from whatever raw material the crew carries. Every system that fails must be restored by crew members who may or may not have the specific training the repair requires, using documentation they may or may not have loaded before departure. Engineering reliability studies for long-duration deep space missions use a metric called mean time between failures, which estimates how often a given component type fails under operational stress. For a complex spacecraft with hundreds of thousands of individual components, the probability of at least one significant failure in any given month approaches certainty. Over 20 years, the crew manages thousands of individual equipment failures. Most are minor. A sensor goes offline, a pump seal degrades, a battery cell drops out of a power bank. These are maintenance events, handled by a competent crew with the right spare parts. The spare parts are the constraint. Every spare part is mass, and mass is propellant. Mission planners must decide before launch which failures are likely enough to justify the launch mass of carrying spare components. Every item not on the spare parts manifest is a potential mission-ending failure, waiting for a moment of bad luck. A three-dimensional printer aboard the ship can fabricate replacement components from raw feedstock. NASA has tested this capability on the International Space Station and confirmed that simple mechanical parts can be printed in orbit. The feedstock is mass, limited. Complex electronic components, optical instruments, and precision-machined parts cannot be printed with current additive manufacturing technology. The crew works around failures that fabrication cannot fix. The life support system gets the most critical redundancy budget. Air recycling, water recovery, carbon dioxide scrubbing, and temperature regulation are single point of failure systems, in the sense that if any of them fail completely and cannot be repaired, the crew dies within days or hours. Every life support component gets multiple redundant backups, which means every backup is mass that had to be accelerated to 20% of light speed. The power system, almost certainly nuclear fission reactors for an interstellar mission, requires the crew to manage fuel rods, coolant loops, and electrical distribution for 2 decades. Nuclear reactor operations aboard a crewed spacecraft with no external support represent an engineering task that has never been performed for more than a few years. The longest continuously operating space reactor, Soviet Buk reactors used on reconnaissance satellites, ran for typically 1 to 2 years before replacement. By year 15 of the transit, the ship is a vessel that has been repaired hundreds of times, running on systems that have been rebuilt, jury-rigged, and modified far from their original specifications. The crew that approaches Proxima b is flying a machine with 2 decades of improvised repairs in its maintenance logs. And through every year of that transit, every repair decision, every equipment failure, and every medical situation, the crew has been making them without any ability to ask Earth for help in real time, because every word they send takes 4.2 years to arrive. Imagine you are the crew commander. A critical system begins showing anomalous readings. You have 3 mission specialists, a flight surgeon, and an engineer aboard. You have the ship's documentation library and a database of engineering reports. You have 20 years of mission training behind you. You also have a communications link to Earth that introduces a 4.2-year delay each way. A question transmitted to mission control on day 1 of the anomaly receives its answer on the day that falls approximately 8.4 years later. The anomaly resolves itself, catastrophically or otherwise, long before the engineers on Earth finish reading your first transmission. This is the confirmed reality of interstellar communication. Light, the fastest signal physically possible, takes 4.2 years to cross the distance to Proxima Centauri. Every transmission, every data packet, every voice message, every distress call sent from the ship travels at light speed and takes 4.2 years to arrive. The reply takes another 4.2 years to return. Mission control at a distance of 4.2 light-years functions as a historical archive, not an active support team. Engineers on Earth can review data the crew sent years ago and send advice that arrives years later. For a system failure developing over weeks, this is operationally useless. For a medical emergency developing over hours, it is the equivalent of no support at all. Astronauts aboard the International Space Station communicate with mission control in real time, with a signal delay of milliseconds. Mars missions face signal delays of between 3 and 22 minutes, depending on orbital position. And even that constraint has driven Mars mission designers to build in dramatically more crew autonomy than low Earth orbit missions require. At 4.2 light-years, the autonomy requirement is absolute. The crew makes every decision, every day, with zero expectation of timely external guidance. The psychological dimension of this isolation exceeds what the numbers alone convey. Humans are social animals, whose cognitive and emotional systems evolved in environments with constant social feedback. Even the most introverted and independently minded crew member operates differently when they know help is 8 years away from being relevant, rather than 8 minutes. A crew member developing a serious illness, a psychotic break, or a moral conviction that the mission should abort has no external authority to appeal to, and no external power capable of intervening. Mission command authority rests entirely within the hull of the spacecraft. The command structure, the medical decisions, the ethical judgments, all sit in the hands of people who are also 20 years into an unprecedented isolation experience. Families left behind on Earth send messages that arrive years after they were sent. A crew member's parent who was healthy at departure may die before the first reply reaches the ship. Births, deaths, marriages, and disasters on Earth arrive as news from the past with no ability for the crew to respond in any meaningful time frame. By the time the crew reaches Proxima b, the world they left may be substantially different from the one they remember. The communication wall is absolute. It is confirmed physics, and it means the crew of any interstellar mission is alone in a way no human beings in history have ever been. What they find at Proxima b, after 20 years of that aloneness, after all of the physical and mechanical and psychological costs of the crossing, is a destination that has one more fundamental surprise waiting, the kind that closes every mission loop with the same answer. Sit with the fuel numbers one more time, because this is where the mission reveals its true shape. To reach Proxima b, the ship burns an enormous quantity of fuel, accelerating to 20% of light speed. If it carries a magnetic sail or some other braking system, It bleeds off that velocity over the final approach and achieves orbit. At this point, the ship has expended the majority of its propellant. The tanks are close to empty, or in some mission architectures, completely empty. A return trip to Earth requires the same sequence in reverse. Accelerate away from Proxima b to 20% of light speed, cross 25 trillion miles, decelerate into the solar system. The energy budget for the return trip is identical to the outbound trip. The fuel for that return journey must come from somewhere in the Proxima Centauri system. If the ship arrives with empty tanks, the crew must either find and process local fuel sources, or the return trip is impossible. There is no resupply mission that could realistically be sent. A support ship launched after the crewed mission reaches Proxima b more than 20 years later. By the time it arrives, the crew situation, whatever it is, has been resolved one way or another for 2 decades. The engineering teams that have studied interstellar mission architectures most rigorously, including the groups behind Project Daedalus and the Tau Zero Foundation's mission design studies, consistently reach the same conclusion in their fuel analysis. A mission that carries enough fuel for a round trip is so massively heavy that the propulsion system required to launch it exceeds any currently conceivable engineering infrastructure. The mission mass doubles, triples, or worse, depending on the propulsion concept, and each increase in mass demands a proportional increase in propellant, which increases mass further. Some mission architects propose Proxima b as a destination where the crew mines hydrogen from a gas planet in the system, runs a fusion reactor to convert it to usable propellant, and stages a return launch from local resources. This requires the Proxima Centauri system to contain a gas planet with accessible hydrogen, an assumption currently unsupported by any confirmed observation of the system's planetary inventory beyond Proxima b itself. A second candidate planet was proposed in 2020, but remains unconfirmed. The practical conclusion, reached independently by multiple engineering groups across multiple decades of analysis, is that a crewed mission to Proxima b, built to the specifications required to get a crew there alive, almost certainly ends at Proxima b. The crew lands. The crew stays. The ship may eventually be cannibalized for surface habitat material. Earth receives transmissions confirming the crew's status every 4.2 years per message. The mission planners who have been most open about this call it a settlement mission, rather than an exploration mission. The crew is not sent to visit. The crew is sent to stay. Their children, if the mission includes a reproductive program, become the first generation born off Earth. The civilization that eventually grows from that seed, if it does, is separated from Earth by an 8.4-year round-trip communication loop and an impossibly expensive travel gap. The mission to Proxima b, under known physics and known engineering, sends people across the largest distance any human has ever traveled, to a world that may or may not be habitable, on a spacecraft held together by 20 years of improvisational repairs, with a crew altered by radiation, microgravity, isolation, and time to answer a question they cannot relay home for over 4 years. And they do not come back. The math has been saying this since the first serious interstellar mission study was published. Every improvement in propulsion, shielding, life support, and communications narrows the gap. None of them close it. And the next layer of the problem, what happens to the human genome when a small founding population tries to sustain itself across generations in a sealed environment, is something the biology of our own species has very specific and very sobering things to say about. The mission designers who accept the one-way conclusion follow it to its logical extension. If the crew cannot return, and if the surface mission is intended to be permanent, then the founding crew will age and die on Proxima b. For the settlement to persist, the mission must include a reproductive program. Children will be born on the ship during transit, or on the surface after landing, who had no voice in the decision that placed them there. This is the generation ship problem, and it sits at the intersection of engineering and ethics in a way that no technical solution resolves. The concept is straightforward as a mission architecture. Send a crew large enough and young enough that natural reproduction over the 20-year transit and the subsequent surface mission produces a population capable of sustaining itself. The founding generation volunteers. Every generation after them inherits the mission without consent. Philosopher and bioethicist Francoise Baylis, along with several colleagues who published analyses specifically on generation ship ethics in the 2010s, argued that placing children into an existence defined entirely by a mission they did not choose raises serious questions about autonomy and moral obligation that mission architects have not adequately answered. A child born aboard an interstellar spacecraft has no option to opt out, no alternative life available, and no frame of reference for what they are missing. Their entire world is the mission. Defenders of the generation ship concept respond that humans have always been born into circumstances they did not choose, including dangerous ones, and that the founding generation carries a moral responsibility to future generations of both the ship and Earth that justifies the imposition. The children born aboard the ship carry humanity's only foothold in another star system. The tension is real and unresolved. Mission architecture cannot dissolve it. What it can do is account for the practical consequences of raising a generation inside a spacecraft. A child born in microgravity or low gravity develops differently from a child born on Earth. Bone density, cardiovascular development, and vestibular system calibration all depend on gravitational loading during growth. If the ship uses rotation to simulate gravity, the engineering requirements for that rotation add mass and structural complexity. If it does not, the children born aboard arrive at Proxima b with bodies that have never experienced planetary gravity and may struggle to function in it. Education, socialization, and psychological development in a closed population of limited size produce a community with dynamics unlike any Earth society. Children have no peers outside the ship's population. Their educational materials are fixed archives from departure. Their understanding of Earth is entirely second-hand, drawn from media and the aging memories of the founding crew. By the time the second generation lands on Proxima b, Earth is a myth to them, a story, a place their parents or grandparents came from, separated by 20 years of travel and an 8.4-year communication round trip. Their loyalty, their identity, and their future are all located on the world beneath their feet. The generation ship is the most honest form of the interstellar mission. It acknowledges the one-way nature directly and designs around it. The founding crew goes knowing their grandchildren will land, and those grandchildren will face a problem the founding crew knew was coming but could not solve before departure: the genetic consequences of a small, closed population reproducing across multiple generations. Population genetics has a concept called the minimum viable population. It refers to the smallest number of individuals a species needs to maintain sufficient genetic diversity to survive long-term without accumulating damaging mutations or collapsing from inbreeding. For large mammals, including humans, the number that appears repeatedly in conservation biology literature is somewhere between a few hundred and a few thousand individuals, depending on the genetic diversity of the founding group. A crewed interstellar mission is not going to launch a few thousand people. The mass constraints are already prohibitive for a few dozen. Mission architecture studies that take crew size seriously, including the landmark analysis published by geneticist Cameron Smith of Portland State University in 2014, calculated that a minimum founding population for a multi-generational interstellar mission needs to be at least 160 genetically diverse individuals to maintain adequate diversity across 200 years of travel. Most mission proposals involve crews of 8 to 20 people. The genetic math for those crew sizes is severe. When a small population reproduces in isolation, the same genetic variants circulate through every subsequent generation. Variants that were rare in the founding population become common simply through the statistics of small sample reproduction. Harmful recessive traits that both parents happen to carry produce children with those traits at dramatically higher rates than in large, diverse populations. The process is called genetic drift, and in a closed population of limited size, it is relentless. Over 3 or 4 generations in a crew of 20, the genetic diversity of the population shrinks significantly. The coefficient of inbreeding, a measure of how genetically similar breeding pairs are to each other, rises. Conditions that are rare in human populations globally become common in the ship's closed gene pool. The solutions proposed involve either expanding the crew to genetic viability, which multiplies mission mass by an order of magnitude, or carrying a library of frozen genetic material, sperm, eggs, or embryos, from thousands of donors on Earth. The frozen library approach allows future generations to introduce new genetic diversity artificially, breaking the drift cycle at controlled intervals. Cryopreservation of human genetic material works. Sperm banks on Earth preserve samples for decades with high viability. Embryo cryopreservation is a standard clinical procedure. The technology exists. The mass required to carry a sufficient genetic library is manageable compared to other mission components. The social and ethical dimensions of a community that reproduces partly through a frozen archive from Earth are less straightforward than the biology. The children produced from archived genetic material have biological parents who died on Earth before the ship arrived at its destination. Their genetic heritage is real. Their connection to the living community aboard is the community that raised them. The identity questions this produces have no precedent in human social history. Cameron Smith's full analysis concluded that a genetically viable mission is possible with a carefully managed reproductive program and a frozen genetic library, but requires mission planners to treat human reproduction as an engineered system with specific targets, timing, and population management, rather than a personal choice. The tension between treating reproduction as an engineering variable and respecting individual autonomy within the crew adds another layer to the ethical complexity generation ships already carry. The genetic bottleneck is solvable in principle. The solution requires the crew to accept a level of managed reproductive planning that no human society has ever implemented. And it assumes the crew remains healthy enough to reproduce, which brings the question of long-duration human biological preservation into direct focus. The cleanest solution to the psychological, genetic, and physiological problems of a 20-year transit is to eliminate the experience of the transit entirely, put the crew in suspended animation, slow their metabolism, stop aging, stop psychology, stop the need for food, water, and social interaction, arrive at Proxima B as fresh as departure day. This is the scenario that decades of science fiction have made feel inevitable. The reality of where suspended animation research actually stands, as of the mid-2020s, is significantly more limited. True suspended animation, defined as pausing biological processes for years or decades and reversing that pause without damage, does not exist for humans. The technical term researchers use is torpor, a state of reduced metabolic activity that some mammals enter naturally during hibernation. Bears, ground squirrels, and several other species drop their core body temperature, slow their heart rate to a few beats per minute, suppress their immune systems, and remain in this state for months. They emerge healthy. Humans do not naturally enter torpor. Human biology lacks the cellular mechanisms that protect hibernating mammals from the consequences of cold temperatures and slowed metabolism. Human cells at temperatures significantly below normal body temperature begin to form ice crystals in the intracellular fluid, and those crystals rupture cell membranes. The damage is extensive and cumulative. A company called SpaceWorks Enterprises has worked under NASA funding on a concept called therapeutic hypothermia induction, drawing on the clinical use of deliberate body cooling in cardiac surgery and stroke treatment, where patients are cooled moderately for hours to days to reduce metabolic demand during procedures. SpaceWorks proposed extending this to weeks or months for space missions, using rotating crew shifts, where a portion of the crew enters mild hypothermia while others remain active. Therapeutic hypothermia for hours is clinically established medicine. Therapeutic hypothermia for weeks is an experimental concept with no demonstrated safety data beyond a few days. For months or years, the cellular and organ-level damage mechanisms are not understood, and no clinical protocol exists. The fundamental barrier is preservation chemistry at the cellular level. Each cell in the human body maintains a delicate balance of ion concentrations, protein configurations, and membrane potentials. Cooling disrupts these balances. Rewarming disrupts them again. Over short periods, the disruption is recoverable. Over long periods, the cumulative cellular damage accumulates past the point of repair. Cryonics organizations that freeze recently deceased individuals preserve tissue structure at extremely low temperatures using antifreeze compounds that replace water in cells before freezing. Whether a cryonically preserved brain can be restored to function remains undemonstrated. Whether the process preserves the information content of a personality is an open philosophical and scientific question. For a crewed interstellar mission, suspended animation remains a research direction, not an available technology. The gap between what the mission needs and what the science provides is wide. The mission cannot wait for the science to close it, because every decade spent waiting is a decade the crew ages past flight eligibility. A 20-year transit with a fully conscious crew is the baseline engineers plan around. And that crew needs to eat, drink, breathe, and function for every day of those 20 years, which brings an entirely different set of calculations into the mass budget. A human being consumes approximately 1.5 pounds of food per day at minimum caloric intake, slightly more than half a gallon of drinking water, and exhales carbon dioxide continuously at a rate that will poison the crew compartment within hours without active scrubbing. Over 20 years, the cumulative consumption of a crew of 8 is staggering. Water is the most manageable of these through recycling. The International Space Station runs a water recovery system that recaptures approximately 90% of water from urine, sweat, and cabin humidity and returns it to potable quality. A more advanced system for an interstellar mission could push recovery rates higher. Some water loss is inevitable, replaced by a stored reserve. Mass required for water is significant but manageable. Air is partially recyclable through the same biological loop. Carbon dioxide scrubbers remove exhaled carbon dioxide using chemical absorbents. Oxygen can be regenerated from water through electrolysis, splitting water molecules with electrical current. The power for electrolysis comes from the ship's reactor. The consumable inputs for the chemical scrubbers must be carried or regenerated. A closed-loop biological life support system using plants and algae to process carbon dioxide and produce oxygen photosynthetically has been studied extensively by NASA and the European Space Agency, and while technically viable, requires significant volume, lighting energy, and careful biological management. Food is the hardest. Growing food in space requires lighting, growing medium, water, temperature control, and crew labor. Research aboard the International Space Station and in Antarctic isolation stations has confirmed that hydroponic and aeroponic growing systems can produce meaningful food yields in closed environments. The caloric output per unit of growing area is limited, and a crew of 8 requiring full caloric sustenance from onboard agriculture needs a growing area measured in hundreds of square feet, maintained continuously for 20 years. A team at the University of Arizona modeled a bioregenerative life support system sufficient for a crew of 8 on a deep space mission in a study published in 2018. Their mass and volume estimates for a fully closed food production system, including lighting, water recycling, growing structures, seed stocks, and processing equipment, ran to several tons of infrastructure and hundreds of kilowatts of continuous power demand. Every kilowatt of continuous power demand over 20 years is a fuel load on the reactor. Every ton of life support infrastructure is mass the propulsion system accelerates to 20% of light speed. The interaction between life support mass and propulsion requirements illustrates one of the core tensions in interstellar mission design. A larger crew improves the mission's genetic viability, psychological health, and operational redundancy. Each additional crew member adds life support mass, food production capacity, water recovery overhead, and power demand. Scaling crew size up to healthy levels pushes propulsion requirements further into the impossible range. Mission designers optimize this trade by minimizing crew size to the smallest number operationally viable, accepting the genetic and psychological compromises that come with it, and accepting that the crew will spend 20 years managing a life support system with no margin for catastrophic failure. The reactor that powers all of it runs for 20 years. The life support systems run for 20 years. The shielding holds for 20 years. And then the crew arrives. And the first question they face, the one that determines whether the entire mission has a future or a terminal endpoint, is whether any of the fuel they need to stabilize their situation at Proxima B is actually available there. Strip the mission down to its fundamental resource problem. The ship arrives at Proxima B with some configuration of near-empty propellant tanks, a worn crew, and a functional set of instruments. The crew needs to assess whether fuel for any future operations exists in the system. Hydrogen is the most common element in the universe. Any star system almost certainly contains hydrogen in some form, whether in the stellar wind, in a gas planet's atmosphere, in water ice on moons or comets, or in trace concentrations across the system. The availability of hydrogen in some form is a reasonable assumption. Processing that hydrogen into usable propellant for the mission's specific engine type is a separate engineering problem. Fusion propulsion concepts, which most serious interstellar mission designs use, burn deuterium, a specific isotope of hydrogen, and in some configurations helium. 3. A rare isotope of helium. Deuterium exists in water at a ratio of roughly 1 part in every 6,000 parts of regular hydrogen. Extracting it requires large quantities of water or hydrogen gas feedstock and an electrolysis and separation system. Helium-3 is extraordinarily rare anywhere except the upper layers of gas giant atmospheres. Whether the Proxima Centauri system contains a gas giant with an accessible helium-3 atmosphere is unknown. The system's planetary inventory beyond Proxima b is not confirmed. Sending the crew on a 20-year mission to a system they may need to mine for fuel, without knowing whether that fuel exists in extractable form, means the mission's return capability, or its ability to fuel surface operations, rests on an assumption that cannot be verified before departure. If the fuel is not available in the expected form, the crew manages with what they have. Surface operations run on stored power from the reactor. The reactor fuel, likely uranium or plutonium, for a fission system, was loaded before departure and is finite. When it runs out, the crew depends entirely on whatever renewable energy the local environment provides. Proxima Centauri is a dim star. Solar energy at Proxima b's orbital distance, despite the close orbit, is lower per unit area than Earth receives from its star, due to the star's lower energy output. Solar panels help, but do not replace a fission reactor as a primary power source for a full settlement operation. The crew that arrives and cannot identify local fuel sources is a crew whose operational horizon extends only as far as their stored energy reserves. Every decision they make from that point optimizes for longevity over capability. Scientific exploration of the surface gives way to survival management. The mission's scientific purpose competes with the biological imperative of the people who carried it there. And the crew's physical condition at arrival, shaped by 20 years of radiation, microgravity, psychological pressure, and mechanical improvisation, is the other half of the operational equation. The bodies stepping off that ship have been through more than any human test program has ever subjected a crew to. What the biology shows about what 20 years of deep space transit does to a person is data that exists only in projection, extrapolated from shorter missions. And the projections are troubling. At 20% of light speed, something happens to time itself. Einstein's special relativity, confirmed by precision experiments to extraordinary accuracy, shows that time passes more slowly for an object moving at high speed relative to a stationary observer. The faster the object moves, the larger the effect. At 20% of light speed, the difference is small but real. For every year the crew experiences aboard the ship, slightly less than the year passes on Earth. The divergence is modest at 20% of light speed. At higher velocities, the effect becomes dramatic. At 90% of light speed, the ship's crew experiences roughly half the time that passes on Earth during the same journey. At 99% of light speed, the time compression becomes extreme. A crew traveling at 99% of light speed for a journey that takes 100 years on Earth experiences roughly 14 years aboard the ship. Most serious interstellar mission designs do not reach 99% of light speed, because the energy requirements to do so are beyond any known propulsion concept. But even at the 20% threshold used in standard Proxima mission profiles, the crew arrives at Proxima b having experienced slightly less than 21 years, while Earth has experienced just over 21 years. The gap is small. However, if propulsion technology improves, and a future mission achieves 50 or 60% of light speed, the time dilation effect becomes a significant factor in the crew's relationship with Earth. A crew that leaves Earth at 60% of light speed and arrives at Proxima b after what feels like 6 years aboard the ship finds that over 7 years have passed on Earth. Friends are older. Technology has advanced. Political realities have shifted. More critically, the relativistic effect compounds on a round trip. A crew that travels to Proxima B and back at high velocity returns to Earth having aged less than the people they left behind. A crew member who left at age 30 and returns after what feels like 15 years of personal time might step off the ship to find that 20 years have passed on Earth. Parents are dead. Children are middle-aged. The world has moved forward in the crew member's absence by a different amount of time than the crew member experienced. This effect, called the twin paradox in its famous thought experiment form, is real and confirmed physics. The global positioning system satellites in orbit around Earth require relativistic time corrections in their software to maintain positional accuracy. Without those corrections, the satellite clocks drift from Earth time in exactly the way relativity predicts, and the position errors accumulate to hundreds of meters per day. For a crewed Proxima mission at accessible velocities, the time dilation effect is a psychological and social reality rather than a mission-critical engineering constraint. The crew returns, if they return, to a world that has aged slightly faster than they have. The longer the mission, and the higher the velocity, the larger the gap. For a mission that does not return, the time dilation effect shapes communication. Messages from the ship are time-stamped by both ship time and Earth time, and the two clocks drift apart over the mission's duration. The crew's subjective experience of elapsed time diverges from Earth's calendar. By the time the crew reaches Proxima B, Earth has marked a slightly different amount of elapsed mission time than the crew has lived. It is a small divergence at 20% of light speed. A reminder, built into the physics of the journey, that the crew has stepped outside the reference frame of the world that built and launched them. In 1973, the British Interplanetary Society assembled a team of engineers, physicists, and designers and gave them an assignment: design the most complete, technically rigorous interstellar spacecraft, possible using only technology that either already existed or was reasonably expected to exist within a few decades. The result, completed in 1978 after 5 years of detailed work, was Project Daedalus. It remains the most thoroughly engineered interstellar spacecraft concept in history. Every system was specified. Mass budgets were calculated. Propulsion performance was verified against known physics. The team published their full design documentation, and it has been studied, critiqued, and built upon by every serious interstellar mission group since. Daedalus was an unmanned probe designed to reach Barnard's star, about 6 light-years from Earth, in roughly 50 years. The propulsion system used inertial confinement fusion, the same principle as a hydrogen bomb, but controlled as a pulse drive. Small pellets of deuterium and helium-3 would be compressed and ignited by electron beams at a rate of 250 pulses per second, producing a continuous fusion exhaust that accelerated the ship to approximately 12% of light speed. The ship design was enormous. The first stage alone, the initial propulsion module that burned for the first 2 years of the mission, contained 50,000 tons of propellant. The second stage carried another 4,000 tons. The total launch mass was approximately 54,000 tons, roughly equivalent to a small naval destroyer. To fuel the helium-3 requirements, the Daedalus team proposed mining Jupiter's atmosphere using robotic balloon platforms. 20 years of robotic mining operations on Jupiter would gather the required helium-3. The fuel acquisition program would need to begin decades before the launch. The design worked on paper. The physics were verified. The propulsion system was theoretically achievable. Every subsystem was specified and cross-checked against known engineering constraints. And the team was explicit about what their design did not solve. Daedalus had no deceleration system. The probe would fly through the Barnard star system at 12% of light speed and continue into deep space. It would have roughly a day to observe its target system. All data had to be transmitted back in that window. For a crewed mission, the Daedalus architecture is a starting point, not a solution. The propulsion system scales in principle, but requires fuel quantities that the Jovian mining program already pushes to its limits. Adding crew, life support, shielding, and a deceleration system to the Daedalus framework pushes the initial mass past any plausible manufacturing and launch scenario. What Daedalus demonstrated, definitively, and with rigorous documentation, is that an interstellar spacecraft is physically possible. The physics do not forbid it. The engineering complexity required is simply beyond anything civilization has yet attempted, by a margin measured in decades of infrastructure development. Every serious proposal since Daedalus has tried to close the gaps the team identified. All of them found new gaps waiting behind the ones they closed. At the top of the propulsion hierarchy, above chemical rockets, above nuclear fission, above fusion, sits antimatter. When a particle of matter meets its antimatter counterpart, both annihilate completely, converting 100% of their combined mass into energy. No other reaction in physics achieves this efficiency. Fusion converts less than 1% of fuel mass to energy. Fission converts a fraction of 1%. Antimatter annihilation converts everything. An antimatter rocket, using proton-antiproton annihilation, would produce an exhaust velocity approaching the speed of light, giving it a specific impulse thousands of times higher than any fusion concept. A spacecraft using antimatter propulsion could potentially reach 60 to 70% of light speed, with a fuel fraction that is, by comparison to fusion systems, small. Travel time to Proxima b drops to around 7 years. The crew arrives biologically younger, less radiation damaged, and psychologically less burdened than any slower mission profile allows. The physics of antimatter propulsion are verified. Antiprotons have been produced and studied in accelerator facilities for decades. CERN produces antihydrogen atoms routinely for research. Antimatter is real, its properties are measured, and the annihilation energy release is confirmed. The production rate is the barrier that ends the conversation. CERN, the largest and most advanced particle physics facility in the world, produces approximately 10 nanograms of antiprotons per year at full operation. 10 nanograms, a billionth of a gram. At that production rate, accumulating 1 gram of antimatter would take approximately 100 million years of continuous operation of the world's most powerful accelerator. A crewed interstellar mission using antimatter propulsion requires grams to kilograms of antimatter, depending on the mission profile and spacecraft mass. The gap between current production capability and mission requirement is so extreme that antimatter propulsion, despite its theoretical perfection, sits outside any credible engineering timeline. Storing antimatter compounds the problem. Antihydrogen must be held in a magnetic trap, suspended without contact with any material surface, because any contact causes annihilation. The longest any team has maintained antihydrogen in a trap is under 20 minutes. Storing kilograms of antimatter for the years required to fuel an interstellar mission requires containment technology that does not exist and whose engineering requirements are not yet fully understood. The energy required to produce antimatter also defeats the mission's energy budget. Antimatter production via particle accelerator is spectacularly inefficient. For every unit of energy the annihilation reaction would release, billions of units of energy go into producing the antimatter in the accelerator. The production energy cost alone would consume the entire electricity output of a continent for years to produce a mission-viable quantity. Future antimatter production technology, using different methods, including pair production from high-energy gamma-ray beams, could theoretically improve efficiency dramatically. Whether that improvement reaches the orders of magnitude required for a mission-viable production rate is an open question that no current research timeline answers confidently. Antimatter is the fuel the mission needs and cannot have. The universe provides the most perfect propulsion chemistry possible, and then makes it impossible to collect. The ship leaves the solar system on a heading for Proxima Centauri. The target is a specific point in space that is itself moving, because every star in the galaxy orbits the galactic center and moves relative to its neighbors. Proxima Centauri is not stationary. It drifts across the sky at a measurable rate, and over 20 years, its position when the ship arrives is different from its position at departure. Mission planners account for this drift in the launch trajectory. The ship does not aim at where Proxima Centauri is. It aims at where Proxima Centauri will be when the ship arrives. At 20 years of travel time and a known stellar velocity, this calculation is achievable with current astrometry. The precision required is extraordinary. A navigation error of 1 degree at launch translates over 4.2 light-years to a positional error at arrival measured in trillions of miles. At that scale, the ship misses the Proxima Centauri system entirely and continues into deep space beyond it, with no ability to correct course if fuel reserves are exhausted. Mid-course corrections require thrust. Thrust requires fuel. Fuel is the resource the entire mission is already minimizing to the edge of feasibility. Mission architects allocate a course correction budget, a fuel reserve held back specifically for navigation adjustments during the crossing. Every correction burn draws down that reserve. The ship's navigation system must maintain positional awareness across 25 trillion miles of open space, with no landmarks and no external reference network. Global positioning systems work because satellites broadcast known signals from known positions. In interstellar space, the ship's position is determined by measuring the angles and velocities of reference stars and calculating position through triangulation, a technique called pulsar navigation in its most advanced form, using the extremely precise timing signals of rapidly rotating neutron stars as navigation beacons. Pulsar navigation is a genuine technology, a system called the Station Explorer for X-ray timing and navigation technology, tested aboard the International Space Station in 2017 and 2018, demonstrated that a spacecraft could determine its position to within a few miles using pulsar timing signals alone. For interstellar navigation, the precision requirements are higher and the signal travel times introduce their own complications. But the principle is confirmed. The deeper navigation problem involves the star itself. Proxima Centauri is a red dwarf, which means it is dim and produces most of its light in the infrared spectrum. At interstellar distances, identifying the precise location of the target star's habitable zone planet from a moving ship requires optical systems of significant capability. The crew needs to identify Proxima b against the star's light as the ship enters the system and execute a precise orbital insertion burn at exactly the right point in the approach. An insertion burn mistimed by even a small margin at interstellar approach velocities results in an orbital trajectory that either escapes the system or impacts the planet. The systems controlling that burn must function correctly after 20 years of autonomous operation and are making a once-in-mission irreversible decision. Every element of the navigation problem is solvable with current technology or near-term development. Together, they require a level of sustained precision over a time horizon that tests every component of the guidance and control system to its design limit. And that is the challenge across every system on the ship. Each one works. All of them must work simultaneously without catastrophic failure for 20 consecutive years. Earth has built a framework for human activity in space. The Outer Space Treaty of 1967, signed by over 100 nations, establishes that no nation can claim sovereignty over celestial bodies, that space activities are the province of all humanity, and that nations bear responsibility for the activities of their citizens in space. The treaty governs satellites, moon missions, and planetary probes. The treaty was written with the solar system in mind. It has no mechanism for a crewed mission that travels beyond the solar system into interstellar space and arrives at a planet orbiting another star. The legal status of a crew operating in the Proxima Centauri system is, under current international law, genuinely undefined. A crew that lands on Proxima b and establishes a permanent settlement is not a national colony under the treaty framework, because the treaty prohibits national appropriation of celestial bodies. The crew operates as representatives of humanity in a formal mission sense, but the practical authority governing their daily operations, their resource use decisions, their internal disputes, and their relationship to Earth exists entirely within the command structure of the mission itself. That command structure is a small group of people, 8 to 20 individuals, operating under mission protocols written on Earth years before departure, with no ability to consult the writing authority in real time. The mission commander's authority is absolute by operational necessity. Disputes that cannot be resolved within the crew have no external appeals process that functions on any relevant timescale. The question of whether a crew member who wishes to leave the mission can do so has no practical answer. Leaving means going where? There is no alternate transportation. There is no neutral territory. The only option available to a crew member who wants out is to remain within the hull of a ship or the boundary of a settlement with people they may be in serious conflict with. Medical decisions, in the absence of a definitive legal framework, raise similar questions. If a crew member requires a medical procedure the flight surgeon believes is necessary, but the crew member refuses, who has authority? The mission protocols define a medical decision chain. The moral and legal weight of overriding an individual's bodily autonomy aboard an isolated spacecraft has no legal body to adjudicate it. These questions become more complex across generations on a settlement. Children born at Proxima b are citizens of what? Exactly. They owe allegiance to whom? The founding mission's charter, written by an organization on Earth 80+ years and 8+ light years away, governs a community that has evolved through 3 generations of lived experience on a different world. At what point does the settlement's own community governance supersede the mission charter? These are questions that human civilization has answered before, in the context of colonial settlements throughout history, and the historical answers are rarely comfortable reading. The ethical and legal void around interstellar settlement is not a gap that law has missed. It is a gap that grows from the fundamental incompatibility of Earth-based governance frameworks with a community that is permanently, physically unreachable. The mission carries no judge, no legislator, and no higher authority. It carries people, resources, and the decisions those people make. Every civilization that has ever formed began the same way. The orbital scan runs. The instruments complete their analysis. The crew reviews the data with the focused attention of 20 years of purpose behind every reading. The atmosphere is 1% of Earth's atmospheric pressure. The surface is a hard vacuum, with superflare radiation hitting it directly. The temperature gradient between the day side and the night side is extreme, and the terminator zone is scoured by permanent category-level winds, where the 2 atmospheric regimes collide. There is no liquid water. The geological record shows the last volcanic activity ended 1 billion years ago. Proxima b is a dead rock. This scenario is not a dramatic narrative device. It is a scientifically credible outcome that multiple atmospheric modeling teams have assigned significant probability to. The superflare erosion history, the uncertainty around the planet's magnetic field, and the unknown geological activity status all contribute to a range of outcomes where habitable and uninhabitable are both plausible. A crew arriving at an uninhabitable Proxima b faces a situation the mission architecture does not resolve. The return trip is, as established, effectively impossible without local fuel sources. The uninhabitable planet does not provide those fuel sources in accessible form. The crew cannot land sustainably. They cannot leave. What they can do is orbit. They can survey, they can transmit everything they have learned back to Earth, knowing the signal takes 4.2 years to arrive. They can document the system in extraordinary detail and provide data that changes humanity's understanding of planetary formation, stellar activity, and the distribution of habitable worlds. And then they face the question no mission planner publicly answers in full. The ship has finite reserves. Life support runs on consumables. The reactor fuel is limited. The crew that cannot land sustainably and cannot leave is a crew managing their survival horizon, while Earth receives their transmissions and cannot respond within any useful time frame. Some mission architects propose that a secondary target, a nearby system that the ship could reach with remaining fuel after the Proxima flyby, be included in the mission architecture as a contingency. Proxima Centauri is part of the Alpha Centauri triple star system, and the primary pair of stars in that system sits about 1/3 of a light year away from Proxima, roughly 500 billion miles. At reduced velocity, with careful fuel management, a ship at Proxima could potentially reach the Alpha Centauri primary system over years of additional travel. Those stars are also orbited by candidate planets. The mission continues. The crew adapts. The original destination becomes a waypoint rather than a terminus. The contingency requires the ship to have arrived at Proxima with enough reserve fuel to execute a second crossing of several light months. Whether that fuel exists depends on the mission architecture's choices made decades before departure. It is a decision that must be baked into the design before launch, by people who will never know whether it was needed. Compile the biological damage profile for a crew member arriving at Proxima b after a 20-year transit. Radiation exposure over 20 years in interstellar space, even with the best shielding currently conceivable, produces a cumulative dose that significantly elevates cancer risk across the entire crew. Some crew members will already carry developing cancers at arrival. The flight surgeon identifies them. Treatment options are whatever the ship's medical supplies allow. Bone density in the hips and lower spine has declined measurably. NASA's research from International Space Station missions shows roughly 1 to 2% bone density loss per month in microgravity, even with vigorous daily exercise protocols. A 20-year transit, even with rotational gravity or aggressive exercise regimens, produces skeletal degradation that physical therapy and resistance exercise slow but do not eliminate at the rates confirmed in shorter missions. Cardiovascular fitness has adapted to an environment with lower gravitational demand. The heart is smaller and weaker than it was at departure. Blood pressure regulation adapted to the ship's environment and struggles to recalibrate when the crew steps onto a surface with gravity, particularly if Proxima b's gravity exceeds Earth's. Vision may be impaired. Confirmed research from International Space Station crews shows intracranial pressure changes from fluid shifts in microgravity produce optic nerve changes and vision degradation in a significant proportion of long-duration crew members. The mechanism involves cerebrospinal fluid redistribution toward the head, which flattens the back of the eye over time. Some crew members lose visual acuity that only partially recovers after return to gravity. Immune system function has drifted from its Earth baseline. Extended isolation changes the microbial environment of the ship, and the crew's immune systems have been calibrated to that narrow environment for 20 years. Introduction to new microbes at Proxima b, even from the ship's own systems in a surface environment, triggers immune responses calibrated to a closed ecology rather than a planetary surface. Muscle mass has declined despite exercise. Tendons and connective tissue have adapted to lower gravitational loads. The crew steps onto Proxima b's surface, which may have higher gravity than Earth, with bodies tuned to a lighter environment. Every one of these physiological changes was anticipated, partially managed, and still accumulated over 20 years because the human body was designed for exactly one environment: Earth's surface. Remove it from that environment for 2 decades and the body optimizes for wherever it is, not where it came from. The crew arrives capable of functioning. They are not incapacitated. They are, however, operating with a significant biological deficit compared to their departure state, and the surface mission that begins the moment they land demands the kind of physical and cognitive performance that the transit has been steadily eroding. There is one more physical constraint that no medical protocol addresses. The crew is 20 years older than at departure. A crew launched with an average age of 35 arrives with an average age of 55. The cognitive performance, physical endurance and recovery capacity of a 55-year-old, regardless of fitness level, differs from that of a 35-year-old in measurable ways. The mission's most demanding operational phase begins at the biological moment the crew is least equipped for it. Before the first crewed mission launches, before a single human being commits to the one-way arithmetic, most serious mission architects agree on one preliminary step: send machines first. A robotic precursor mission to Proxima b, following the breakthrough Starshot architecture, or a more capable derivative, would accomplish something the crewed mission cannot do for itself: reduce uncertainty before the crew commits. A gram-scale probe flying through the Proxima Centauri system at 20% of light speed has limited observation time. A more capable robotic mission, heavier and slower, using a fusion propulsion system to actually decelerate into orbit, could map the system thoroughly. It could characterize Proxima b's atmosphere, measure the surface radiation environment, identify water sources, assess the geological activity level, map the terminator zone in detail, and transmit all of that data back to Earth. The data transmission arrives 4.2 years after the probe sends it. Earth evaluates the findings. Mission planners determine whether a crewed follow-up mission makes scientific and operational sense. They choose a landing site. They identify risks. They design the crewed mission around confirmed surface conditions, rather than probabilistic models. The case for robotic scouts is not just philosophical. It is operational. A crewed mission arriving with confirmed surface data makes every landing decision with actual intelligence rather than best estimates. The difference between landing on a confirmed, temperate, water-bearing surface and landing on an assumed one is the difference between a mission that succeeds and one that ends in the first week of surface operations. The argument against robotic scouts first is the timeline. A robotic orbital mission to Proxima b, using fusion propulsion to decelerate into orbit, travels slower than a starshot flyby and takes longer to design and build. Launch to arrival might take 50 to 100 years using realistically projected propulsion development. The data arrives 50 to 100 years after launch. A crewed mission based on that data launches another 50 years after that, accounting for development time. The total timeline from decision to crewed landing extends over a century. Some mission advocates argue that the urgency of interstellar expansion justifies accepting more uncertainty to compress the timeline. Others argue that sending humans into a system with fundamental unknowns about surface habitability is ethically indefensible, given the one-way nature of the mission. The scientific community, evaluated across the published literature, leans heavily toward robotic precursors. The engineering community, working the mass and fuel numbers, agrees that a robotic mission is far more achievable in the near term than a crewed one. The robotic scout case does not resolve the human mission's challenges. It frames them with data instead of projections, and the humans who eventually go, if they go, will go with better information than any crew can have by going first. The question is whether humanity is patient enough to wait for that information before committing the people. Every generation of engineers who studied interstellar travel found the same gaps. Every generation also found those gaps somewhat narrower than the previous generation had. Propulsion efficiency has improved across every technology class over the past century. Computing power has increased to a degree that no mid-20th century engineer would have considered plausible. Material science has produced substances with properties that seemed impossible a generation ago. The question is whether the gaps in interstellar mission capability close faster than the urgency driving the mission grows. Physicist Gerard O'Neill, working in the 1970s, argued that waiting for technology to mature before launching was always the rational choice in engineering, because a mission launched with inferior technology and high cost could be superseded by a better mission launched 10 years later with far less effort. The second mission, using improved propulsion and life support technology, arrives before or around the same time as the first, one despite launching later, because it is faster. Applied to interstellar missions, this argument suggests that launching a crewed mission with current technology would be not only brutal for the crew, but potentially unnecessary if a generation of propulsion breakthroughs produced a faster ship within 50 years of them. Original launch date: the better ship could catch the first one in transit. The counter-argument is that propulsion breakthroughs of the magnitude required, specifically moving from fusion propulsion at 12% of light speed to something approaching antimatter performance, are not incremental improvements. They are categorical jumps that require either entirely new physics or engineering infrastructure that does not currently exist and whose development timeline is genuinely uncertain. Waiting for a breakthrough that may be 50 years away could mean waiting for one that is actually 150 years away. During that wait, every year that passes is a year that the existential risk arguments for interstellar expansion, specifically the case that humanity should not remain a single-planet species, go unaddressed. The honest answer is that the technology trajectory is real and measurable in some areas, while completely unclear in others. Miniaturization continues to improve. Computing power continues to grow. Materials science produces increasingly capable lightweight structures. Propulsion, the core limiting factor, shows theoretical pathways toward improvement, but no confirmed breakthrough on a defined timeline. A mission launched with current technology solves the problem of going now and pays the full biological and engineering price for it. A mission launched in 50 years may be dramatically cheaper in every human and engineering cost if the propulsion gap closes, or it may launch under the same constraints if it does not. History suggests that engineering problems, once framed with sufficient precision, tend to get solved. The specific timescale for that solution is the part history has never predicted reliably. There is a moment in every serious interstellar mission planning discussion where the engineering tables close and the fundamental question sits on the table unanswered. Is it acceptable to send human beings on a mission from which they cannot return? The engineering case has been made in exhaustive detail across 30 chapters. The physics say the mission is possible in principle. The biology says the crew will be damaged by the journey. The psychology says the isolation will alter them. The fuel math says they stay at the destination. The genetics say the founding population is barely viable. The surface conditions say the destination may not be what anyone hoped. And humans keep trying to design the mission anyway. The motivation comes from multiple directions simultaneously. The survival argument holds that a species existing entirely on a single planet is permanently vulnerable to extinction from any planetary scale event, whether geological, astronomical, or self-inflicted. Distributing humanity across star systems eliminates that vulnerability. Each settlement becomes an independent survival node. The logic is actuarial and cold. Enough settlement missions mean some succeed, and those successes persist across timescales that dwarf any individual mission's cost. The exploration argument holds that human beings have always accepted extraordinary personal risk to extend the boundary of the known, and that the compulsion driving that behavior is not separate from what makes humanity cognitively capable. The willingness to go is the same trait that built civilization. The meaning argument, less comfortable in engineering documentation but present in the statements of every serious mission advocate, holds that the mission has value independent of its practical outcome. The crew that reaches Proxima b and transmits confirmed observations of an alien world, even if they never return, has done something that changes the human story permanently. Every transmission they send back is a new data point in humanity's understanding of whether it is alone. Against these arguments sits the weight of what the mission actually asks of the people who go. 20 years of physical and psychological damage, permanent separation from everyone they knew. Children born into a mission they cannot leave. Death on a world under a dim, violent star, billions of miles from the place their species evolved. The engineers who work on these proposals are not naive about the cost. They document it. They model it. They publish it alongside the propulsion equations and the mass budgets. The cost is part of the proposal, not hidden from it. What makes interstellar mission planning philosophically distinct from other extreme human endeavors is the completeness of the commitment. A mountaineer turns back. A polar explorer is rescued. A combat soldier returns home. The crew of an interstellar mission goes entirely, permanently, and beyond any mechanism of recovery. The decision, once executed, is the most irreversible choice any human being has ever made. The people willing to make that choice exist. They are not mythological. Surveys of astronaut candidates and aerospace professionals consistently find individuals for whom the mission, as described in its full brutal detail, remains a choice they would make. The question of whether those people should be sent is one that engineering cannot answer. Every path through this mission ends at the same place. The distance to Proxima b is real. The physics of crossing it are confirmed. The engineering requirements are documented in enough detail that the gaps are precisely identified rather than vaguely dreaded. And when you stack every gap on top of every other gap, what appears as a mission that is not impossible, but that demands a version of human civilization and human technology that does not yet exist. The propulsion system to reach Proxima b within a human lifetime is theoretically available through nuclear fusion, but the fuel infrastructure to build and launch it does not exist. The braking system to stop at the destination is physically sound but requires structures of a scale never attempted. The radiation shielding sufficient to protect a crew over 20 years adds mass that defeats the fuel budget. The life support system capable of sustaining a crew for 20 years in a closed loop exists in prototype form and has not been demonstrated at mission duration. The human body degrades under the conditions of the crossing despite every intervention available. The psychology of the crew changes under the weight of 2 decades of isolation. The ship accumulates 20 years of mechanical entropy with no external support. The destination may or may not be habitable by anything alive on Earth. And the crew, if they arrive, stays. Every engineering team that has formally studied this mission has found these same problems. Every proposal for solving one problem creates a new version of another. The tyranny of the rocket equation, the radiation environment, the biological constraints, and the one-way fuel math form a closed system of obstacles that each solution partially addresses while shifting the burden elsewhere. What these studies also show, consistently and without exception, is that each generation of proposals gets closer than the last. The gap between what the mission needs and what the technology provides has narrowed across every decade of serious study. The fusion propulsion concepts of the 21st century are more advanced than those of the 1970s. The radiation shielding materials available today are better than those available when Project Daedalus was designed. Closed-loop life support has moved from concept to tested hardware. Navigation precision has improved dramatically. The mission to Proxima b is a moving target in the right direction. The timeline for closing all the gaps simultaneously is the uncertainty that no one can quantify with confidence. What is certain is this: it sits at 4.2 light-years, orbiting a violent red star, possibly holding an atmosphere, possibly holding water, possibly holding something that no instrument on Earth has ever been close enough to detect. Every day that passes, the telescopes looking at it improve. Every year, the propulsion concepts become more refined. Every decade, the engineering proposals become more specific. The mission to Proxima b will be attempted. The physics allow it. The human drive that calculated these distances, built the equations, designed the ships, and ran the numbers until the gaps became visible rather than hidden, will eventually close those gaps or find a path around them. The crew that launches will go knowing the full cost. They will go knowing they will not come back. They will go anyway. The math keeps saying no. Humans keep doing the math.